presentation is going to come from BlazingSQL, Tom Drabas and Felipe Aramburu.
Hello, everyone. Thanks. Can you guys hear me?
Can hear you. Are you going to be presenting the slides, Tom?
Yes.
Okay, fantastic.
I'm just about to actually start that. Can you guys see this? I think I'm sharing my screen right now.
Yes, it's perfect.
Awesome. So thanks very much for the introduction. As you mentioned, we are BlazingSQL or SQL, depending on who you ask. We are GPU-accelerated SQL engine, right? So this is going to be a very, very brief introduction into what we do. BlazingSQL is a SQL engine for high-performance GPU clusters on massive scale. So we thought that would fit quite well within the realm of HPC. What we do is we do operational analytics. So if you have massive amounts of data, we use GPUs to speed up things, to give you the familiar tools of SQL, of expressing yourself using SQL, and bring the massive speed that GPUs enable. So very, very quick historical note. Back around roughly 15 years ago, we've seen the rise of Hadoop that enabled us to process massive amounts of data, ever-growing data, and it took those computations from hours, and and it took hours to days to process that. It used a GPU fleet to manage all of these computations, this data processing. Around 2009. Bunch of guys that were not very satisfied with the performance of Hadoop released Spark. Spark brought the in-memory computations, so you no longer need to offload stuff to disk every single time you finish one piece of processing. You can do most of the time in memory, and it reduced the compute time from minutes to hours. Still, using mostly GPUs, using mostly CPUs these days is already taking its toll, and the computations take hours, sometimes days, to handle the massive scale of data that we currently see. So around 2018, Rapids was the newcomer into the market of GPU data analytics, bringing the GPU into the equation. So we can right now take a large, massive data and then enable this second or sub-second processing in certain times and to scale in 2 minutes. We have some examples of that where we partnered with our partners to reduce the compute times from days to literally interactive minutes like queries. We use shared memory, so we can span across multiple GPUs, and it's designed to enable pretty much anybody to jump into the GPU world without necessarily learning how to use CUDA. BlazingSQL is a part of the Rapids ecosystem. So BlazingSQL is this de facto engine, SQL engine for anything that runs on GPU. Rapids brings to the market the cuDF, which is an equivalent of data frames. It's kind of like a table, if you think that way. And BlazingSQL builds on top of that. So we can take a cuDF, register that with our engine, and you can run SQL queries against that data that sits in a cuDF. QML, on the other hand, it brings the machine learning to the whole stack. And cuGraph, if you deal with graph analytics, you can process graph data and do graph analytics using cuGraph. We've seen speed ups in terms of if you run PageRank, for instance, in well into 1,000, 2,000 times faster than if you do the same thing on the CPU. What enables all of this is Apache Arrow. Apache Arrow is the framework that allows you to manage the memory objects from pretty much any computer language that exists. So C++ will use the same objects as Python, and Apache Arrow Rapids brought it onto the GPU. So anytime you do anything with the memory, with the data that sits on the GPU, we talk to the Rapids using Python interface but all the manipulations, all the data manipulations, all the data transformations happen in a C++ layer, and CUDA layer, and CUDA kernels. Apache Arrow allows us to take the advantage of not needing to copy the data and convert the data to different representations in order to take that massive speed and enable that massive speed. So Rapids brings this familiar Python data interface. So if you're familiar with pandas, if you're familiar with scikit-learn, if you're familiar with NetworkX for GPU for graph computations, or if you know SQL, you can jump pretty much straight away into the GPU realm and enable that massive speed. We also, we enable the Haldor acceleration, so it's really fast because of the usage of all the, CUDA. So everything that runs using Rapids or using BlazingSQL, once the data is loaded into the GPU memory, it never leaves. So all the computations, any transformation, any action you do on your data happens on the GPU, and is also cost effective. So if you think about the speedups that we get. Even the GPU per hour unit might be more expensive than an equivalent of CPU computation. Because of the massive speed up that you get, the actual total cost of ownership is much reduced. And it's also very easy, so easy to get started. Most of the pandas, most of the Rapids APIs model after pandas, or all the other familiar tools from the PyData ecosystem. So it's much easier to get started and tap into this powerful speedups. Some of the things that don't fit on a single machine needs to be distributed. Rapids uses Dask to handle the distribution of the data, so you can scale it up to thousands of machines, all of which can be equipped with GPUs. BlazingSQL is no different, and I'm going to hand it over to our founder, Felipe Aramburu, who's going to walk us through the experience that we went through in order to enable UCX to handle those communications between the nodes in BlazingSQL. So Felipe, off to you.
Thanks, Tom. Hi, I'm Felipe. So I'm going to talk a little bit about UCX real quick and explain how it fits into Blazing and give it a little explanation of what Blazing is under the hood. For those of you who don't know UCX, it's a collection of libraries, some that manage transport to be able to abstract a message that you're trying to send across different transports. So it can use TCP, or if it's sending data between two GPUs, it can use NVLink, it can use InfiniBand. So it allows you to write one kind of application layer that can not only leverage these different communication layers, but they can actually pick the optimal one for you. Most of our work is concentrated in the UCP layer, which is the high-level API for accessing these different transports and some of the services. Can we go to the next slide, Tom? So to give you a quick idea of what Blazing is Blazing is it's mostly written in C and C++. Python is the user interface, so to speak. That's how the user interacts with it. And we use Dask for launching all of these different Blazing contexts on a cluster. So Dask is what kind of starts up a Blazing context and allows you to do things like register file systems, if you want to connect to HDFS or S3, things like that. And it is kind of what keeps that context alive. Once you actually get into the part of, executing queries, however, all you're really doing is generating a graph and then executing that graph. So all of the execution, transformations, the communication, the file IO, all that happens in the C++ layer to avoid, to be able to, one, leverage not just the GPU, but the CPU threads as well, and do a lot of multi-threaded things that can be a bit more challenging with Python. And so if we go to the next slide, we can kind of look at what a blazing execution graph looks like. So one, it's homogeneous. So we have the same graph on every single node being executed. This allows us to, when we are distributing, to have every single node know exactly where it's supposed to route its message on another node without having to, have different plans being executed on every single node. They're distributed, they're running in parallel. So even within a node, multiple of these kernels can be running at a time. Here, we kind of have an example of, at the very top, we have a table scan. So we're scanning a table from some file system, like it'd be S3 or HDFS, reading that information into a QDF, and then we put that in a cache. Every kernel in Blazing is connected by a cache. This is what allows us to handle bigger than GPU, bigger than CPU memory processing. The cache is basically whenever a task gets executed by one of these kernels, it allows us to make sure that we can, put that information either in the CPU or on disk if we know that resources are getting tight and we want to keep those resources available for things that we're going to be operating on more immediately than things that might have to wait a while. Can we go to the next slide? So the kernels are either leveraging calls directly to the libqdf API, which is the C++ layer of QDF, or is using other kernels that have been written for the GPU, but all those transformations are happening on QDF data frames. Obviously, the CPU and disk representations aren't QDFs, but they are things like ORC files or CPU or exact memory copies of what the GPU representation is, so that we can go to and from the QDF very, very quickly. They're executing in parallel, and for distribution, we have a couple of primitives that we've implemented in UCX for sending, scattering, and broadcasting informations. And these messages are if we go to the next slide, these messages that we're sending are really just QDFs with a little bit of routing metadata to let it know when it gets to the other worker where it's supposed to be sent. So the way that it normally works, right? If we're going to be doing a join is actually broken up, and it's broken up into more than two kernels, but for simplicity's sake, we've just made it two here. And so you have kind of a distribution phase where you know that you're going to perform a join between two very large tables, and you have to break that up. So say it's an inner equality join, you can do a hash partition here in order to distribute these joins all to single nodes, so you can perform the whole join on that single node. In this case, so whenever you want to send a message, a kernel will basically add this message to an output cache, and there's a process which is waiting for those messages to get added when they, that is basically listening to that output cache for messages that get added, and then sends them to the other worker via UCX. And then the other worker routes that message directly to the cache that is then going to get fed into the join process. Yeah, can we go to the next slide? So yeah, just reiterating what a message actually is for us. It's just metadata that routes a QDF. And so the interesting thing is that this transportation layer is runs in parallel, is implemented in C and C++, and has some very simple Python bindings. So other users, people, or library could at some point start leveraging this to send around QDFs quickly via UCX, leveraging only the C and C++ layer. So this could really help performance of different processes that are trying to send around these QDFs, especially if they're working on the C and C++ APIs. Obviously, with Python, there's a good reason to use Dask UCX, which already has other primitives built in. But yeah, that's I think we can go to the next slide now, Tom.
Yep, I think that's my part now. So thanks, Felipe. That was great. So I hope that was a good introduction into how the internals of BlazingSQL work, and also how Rapids is actually using the communication between different nodes. So in terms of practical applications, everybody's talking about COVID. We cannot be much different. We actually partnered with Oak Ridge Labs to help with their molecular docking simulations. So one of the researchers at Oak Ridge Lab, they run a simulation over 2 billion molecules in order to search for a cure for COVID-19. So if you get sick, you can actually help to get better in surviving COVID. The data was massive. So if my memory serves me, it was way over 4 terabytes, so 4 petabytes of data. And then every single time they run a query against that data set, it would take days running on Summit. BlazingSQL partnered with Oak Ridge, and we deployed BlazingSQL with Rapids stack on top of Summit. And immediately, within a few days from that happening, the researchers were able to take that massive data set and run the questions against that data set in a matter of minutes. So we're talking about the speed up of coming from days to literally minutes, 20 minutes, 15 minutes, 13 minutes, whatever that time is. But there was literally like a paradigm shift coming from days waiting for the results to come back to literally having this interactive dialogue with the data that you wanna communicate with. So this enables enables you to actually have this more immediate results, and then enables the avenues of research that would not be able beforehand. Because when you start thinking about, okay, well, what if this happens? What can I do then? If you need to wait a couple of days, chances are you might have forgotten about what you were thinking at that point in time. If you have this interactive dialogue, you can really quickly iterate over different questions and then arrive at the better solution much quicker. If you want to start, we have a couple of ways to start using BlazingSQL and Rapids. The easy way, you can go to Anaconda or Docker Hub. Rapids AI channels right now bring over as well the BlazingSQL. So if you install Rapids AI through Anaconda, or if you download the Docker image, BlazingSQL is already there. If you want to use a turnkey solution, we offer Blazing notebooks that allow you to bring in, scale up, create clusters anywhere between 1 and 64 GPUs. All of these right now we run mostly on AWS, but this solution is deployable on pretty much any public cloud or private cloud, or a hybrid as well. And as I mentioned before, we deploy that on Summit, so this is also deployable on any HPC, pretty much on any HPC environment. In the cloud, we offer a very easily scalable solution. It is a multi-tenant, so you have the control who gets how much resources from the resources that you have under your management, and you can bring and create your own environment. So if you use different packages to process your data, you can also create a data environment and then bring it over to our stack. And that's pretty much it. So this is very quick introduction to BlazingSQL. If you want to, you can ping us directly on through these emails, or find us on Twitter. But if there are any questions, we would be happy to take them right now.
Thank you, Tom. And thank you, Felipe.